Hello. So now what we are moving on to is we're moving back a little bit because we're going to be talking about the mole again. And what we're going to do in this chapter is really just focus on the mole and sort of update it with what we have learned about chemicals, about covalent compounds and ionic compounds. And the next chapter is where we put chemical reactions and chemical quantities together in something that's called stoichiometry. So, what we're doing in this first section is going over the mole, reviewing what that is, but then also adding in this component of mass to it. So this was how we started talking about the mole. We said it was really useful because when we as chemists want to count number of atoms, that's going to be very difficult because atoms are so small. So what we have learned how to do is to count atoms by mass. And so this is an example of how we can count by mass and also reviewing what we call dimensional analysis. So we have literally been doing this on every single exam that we have had so far this year in terms of oldies but goodies. And still about 50% of us have not learned what dimensional analysis is or our conversion factors. That is going to be important for us to know moving on. So you should review that if you are not sure. In dimensional analysis, we will always have something called conversion factors. Two things that are equal to each other, but because they have different units, they have different numbers, but they're still equal to each other. So like a dozen apples is the same thing as 12 apples, but because one has the unit dozen and one has the unit apples, the numbers can be different. Or 2.0 kilograms equals 1 dozen apples. Those are two different units. Kilograms and dozen are different units, and so they have different numbers associated with them, but the amount is the same. So the question says 100 kilograms of apples is delivered to the school. How many apples are in the delivery? Think of how long it would take if you had to count out all of those apples. But if we know these two conversion factors, we can just do a quick calculation to figure that out. When we do these problems, we always circle the do and underline the clue. And we take the number that we want to convert and we put it out front. And then we draw a parenthesis. We use one of these conversion factors is going to go into our parenthesis, making sure that the unit out front is equal to the unit down bottom. Those two must match always. So the only time I have kilograms in all my conversion factors is that 2.0 kilograms is equal to 1 dozen apples. If I stopped here, my answer would be in dozen apples. I don't want that. I want actual number of apples. Still, my conversion factors should make it so that they cancel out. The diagonal down needs to match. On the bottom, I'm going to put 1. On the bottom, I'm going to put 1 dozen apples. And that, of course, is equal to 12 apples. Right? So if I look at it, right, a dozen apples and a dozen apples, those units are going to cancel out. And so now in my calculator, I just go piece by piece by piece. So I plug in 100 and then I always multiply by the top and then divide by a bottom. This is not anything different than regular fractions. When you have fractions, that top is multiply and that bottom is divide. So in my calculator, I'm going to do 100 times 1, which I can skip, divided by 2, times 12 divided by 1. The answer that I'm going to get is 600 apples. And I'm not going to really worry about significant figures at this time. Significant figures are all about measurements and instruments. We're not talking about an instrument here. We're counting number of apples. Here's another question, very similar, but it's just going backwards in a little bit different way. If you want to see if you can do this on your own, so try this on your own, and then we can try it together. It says the cafeteria needs 300 apples to make pies for the 4th of July. How many kilograms of apples should they buy? So circle the do, kilograms of apples. That's what this question is asking me to do. Underline the clue is those 300 apples and all of those conversion factors. So 300 apples always goes out front. Now we pick our conversion factors using the idea that whatever unit is out front, I need to match that diagonal down. So this told us that 12 apples were in 1 dozen, and then 1 dozen is what, 2.0 kilograms, right? Because I want to know kilograms. So now when I plug this into my calculator, the apples units will cancel because they're the top and the bottom of a fraction. The dozen units will cancel because they're the top and bottom of a fraction. So I do these problems twice, once with the units and then once with the numbers. So in my calculator, I'm putting 300 divided by 12 times 2, and that comes out to be 50.0 kilograms. So the cafeteria knows that it needs to order 50 kilograms of apples in order to get enough apples for all the pies. Now, that's just a review of dimensional analysis in general and how we can use mass in order to count. We're going to put those together in more chemistry terms, in terms of the mole. So we learned way back at the beginning of the year that 1 mole of a substance was a way to talk about a lot of the little particles. It was equal to Avogadro's number, 6.022 times 10 to the 23 particles of that substance. So if we're talking about cobalt, the smallest unit of cobalt is an atom of cobalt. So we would say that 1 mole of cobalt is 6.022 times 10 to the 23rd atoms of cobalt. But if I'm talking about water, the smallest unit of water is a molecule of water. So then I would say 1 mole of water is 6.022 times 10 to the 23rd molecules of water. A mole and a molecule are not the same thing at all. Not the same thing at all. You plugged this number into your calculator, theoretically, saved it as alpha M. That will come in handy when we start doing these calculations. So a mole is this giant number, right? Avogadro's number is a very, very large number. But since atoms are so ridiculously small, if you have a mole of atoms of copper, for example, look it's actually not that much copper, right? There's not actually that much copper in there. A mole of water molecules is about a sip of water molecules, so it's actually not that much. And then this table just reminds us that the number of, if we're talking about an element or a compound, a mole represents the number of the smallest particle of that. So if I'm talking about copper or nitrogen, it would be an atom. If I'm talking about nitrogen gas, so that would be a molecule of nitrogen or a molecule of water or a molecule of sucrose. And if it is an ion, I would say 6.022 times 10 to the 23rd calcium ions, if I'm talking about the literal ion. Or if I'm talking about the ionic compound, I don't use the word molecule, but I use the word formula unit. Okay. So now we have some practice problems with the mole and converting between moles and particles. And you see the little show me graphic. That means that there is a video of me doing this problem online. I know you're going to do this problem right now, but if we go to, or if you eventually transition to when we are doing notes in class, this will be good if you miss something. So the question says, how many atoms are in 3.67 moles of cobalt? So circle the do. Question's looking for atoms. Underline the clue. Moles of cobalt. I take my number that's given to me and I write it out front. The abbreviation for mole is MOL. You just get to leave off the E. And please remember that cobalt is a capital C and a lowercase o. Not a capital C and a capital O. I'm going to need to start taking points off for that. Capital C and capital O is carbon monoxide. It is something different. So I am not going to make a judgment if you are making a typo or if you don't understand. So please make sure cobalt is a capital C and a lowercase o. Now the conversion factor that I'm going to use is 1 mole of anything is equal to 6.022 times 10 to the 23rd, and I'm just going to use the word particles because depending on what I'm talking about, it could be the word atoms, it could be the word molecules, or it could be the word formula units. In this case, right, so I put the unit of mole on the bottom, so they're going to cancel out. 6.022 times 10 to the 23rd. What's the smallest particle of cobalt? Well, that would be an atom of cobalt. So that number goes with 6.022, Avogadro's number, goes with the words atoms, molecules, or formula units. What a lot of students will start doing is 6.022 times 10 to the 23rd mole. That is not true. They're like, hasn't been that many. So 6.022 times 10 to the 23rd moles of something means moles squared. That is a ridiculously large number. So that is not true. When you plug this into your calculator, right, if you have saved Avogadro's number in there, 6.022 as alpha m, all you need to do is 3.67 times alpha m. And then you will get an answer, and now we do need to worry about significant figures. The number that's given to us, we need to use our significant rules to figure out how many. 6.022 is a number that has 4 significant figures. And so our answer will have 3 because we use the lowest number. And we get 2.21 times 10 to the positive 24, and that would be atoms of cobalt. The next question says, how many moles contain 5.73 times 10 to the positive 26 molecules of water? So I take the number that's given to me, 5.73 times 10 to the positive 26 molecules. If you want to abbreviate that word, it's MOLEC. And I know that 1 mole, right, this is another way to remember how to set up my parentheses. Whatever I'm converting to is going to go on the top of my conversion factor parenthesis. So this question is asking me how many moles. So 1 mole goes on top, and Avogadro's number is 6.022 times 10 to the 23rd. Remember, molecules, that word can be atoms, molecules, or formula units. So in my calculator, 5.73, and now we need to use scientific notation here. Remember, we use second and then the comma to get a small but uppercase e. And then I put in whatever the e stands for, exponent. I put in the exponent of 10, which would be 26. My calculator should give me 952 moles of water. Try this, like actually plug this into your calculator. One of the problems this year is that as we are doing these video notes, you are not doing these calculations yourself. You're relying on me to do the calculations for you. And then when the test comes, you've never actually used a calculator. You need to practice this. Students often will not get using Avogadro's number or using scientific notation in their calculator correctly. The next question, how many molecules are in 0.2569 moles of carbon dioxide? Underline the clue, circle the do. We're looking for molecules. Take the number that's given to me, 0.2569 moles of carbon dioxide, right? 1 mole on the bottom. The rule that is really the most important rule to follow is whatever unit is out front needs to match the unit on the bottom. And whatever I'm converting to goes on the top, 6.022 times 10 to the 23rd molecules of CO2. I plug this into my calculator and I get 1.547 times 10 to the positive 23 molecules of CO2. 4 significant figures here because the number that's given to me has 4. 6.022 has 4. Remember that number 1 is like a counting number. That doesn't count. We have defined 1 mole to be 6.022 times 10 to the 23rd. So therefore my answer just has 4 significant figures because that's the least number of significant figures in the problem. And then the final question says, how many moles contain 2.009 times 10 to the positive 22 atoms of helium? So I take the number that's given to me, I set up my parenthesis, 6.022 times 10 to the 23rd atoms of helium, put 1 mole on top, right? Whatever I'm converting to goes on top. I divide those 2 numbers. Please try this in your calculator. This is a calculation that students get wrong all the time. 4 significant figures because both of those numbers have 4 significant figures. So you need to round your final answer.